Chapter 2, Alkanes and Cycloalkanes, Conformational and Geometric Isomers. Here are several types of hydrocarbons. They're compounds that only contain carbon and hydrogen atoms. You may have alkanes with all single bonds, alkenes with double bonds, alkynes with a triple bond, or arenes, which are six-membered rings with an alternating sigma and pi bond system. They're also termed aromatic, and we'll get to those later in the course. So let's look at the structure of alkanes. As I said, they're saturated hydrocarbons that contain a maximum number of hydrogens possible for the number of carbons present. And you can follow the general formula of CnH2n plus 2. This means that every carbon is sp3 hybridized, and this results in a bond angle of 109.5 degrees. So continuing a presentation of the structure of alkanes, they can come in two forms, normal or linear, or branched. Branched alkanes have branched branches, therefore the number of isomers grows quickly depending on the number of carbon atoms. And please note that the structures on this slide, they are just line drawings, and they contain what are called implicit hydrogens. And when you start out drawing structures, I advise you to use carbons and hydrogens. Fill the hydrogens in because it's much easier for you to keep track of things. Again, this slide illustrates the increase in molecular formula regarding the increase in number of isomers. So for CH4, which is methane, there's only one possibility. And moving up to C4H10, which is butane, we now have two isomers possible for that. This slide gives some information on the nomenclature of alkanes. There'll be more through this presentation as well. But please note that a CH3 group is termed a methyl group, a CH2 group is a methylene group, and a CH group is a methine group. So you'll hear that terminology throughout this course. I'd like to now talk about intermolecular forces in alkanes. And these are related to boiling points and solubility, and the strength of the interaction between molecules is dependent upon the shape of the molecule. There are three types of intermolecular forces, and they decrease by the strength in this ranking. Number one is hydrogen bonding. Two is dipole-dipole interactions. Number three are van der Waals or London dispersive forces. So let's look at hydrogen bonding first. This is a complex interaction, and it includes dipole-dipole as well as orbital interactions. And these are the strongest of the intermolecular forces and range from 5 to 25 kilojoules per mole. So hydrogen bonding, it occurs between an electronegative atom, typically OH, NH, or FH, a halide. The more the electronegative the atom, the stronger the interaction. And you're probably familiar with this type of interaction with a water molecule, where you can see the water molecule written as HOH. The oxygen, being electronegative, is pulling electron density towards itself, resulting in a slightly negative charge. This then creates a slight positive charge on the hydrogens. If you then move over to the structure on the right, you can see how the lone pairs on the oxygen will interact with the slightly positive hydrogen on another water molecule. Finally, on this slide, we can see that it also happens for ammonia, where the nitrogen has a lone pair and will be slightly negative, resulting in slightly positive hydrogens and giving us our hydrogen bonding. Now, dipole-dipole forces arise from the attraction of oppositely charged atoms. And in organic molecules, they result in the presence of CX bonds, where X is more electronegative. Typically, X is is depicting a halogen. So this slide presents dipole-dipole interactions. And this will be important in terms of the polarity and so forth of a organic molecule. So you can see in the upper left here we have chloromethane. That's a carbon with 3 hydrogens and 1 chlorine attached. So the chlorine is the electronegative atom, right? And the hydrogens are the slightly positive portion of the molecule, resulting in a net dipole towards the chlorine atom. And there are several other examples on this slide. So the weakest of the intermolecular forces are van der Waals forces, and it arises from a movement of electrons within a molecule to create a dipole moment in adjacent molecules. They're very brief. They disappear when the electrons continue to move throughout the molecule, and they're, in comparison to the hydrogen bonding, they're only 2 to 5 kilojoules per mole. The influence of structural effects on intermolecular forces are presented in the next few slides. You can see here that the 2,2-dimethylpropane has a boiling point of 10 degrees, while pentane, or N-pentane, a linear chain, has a boiling point of 36. This is due to the proximity or the packing of the molecules next to each other. And now we can see that alkanes, because they're just carbon and hydrogen, they really have the boiling point is going to increase with increasing size. Now, dipole forces are much stronger if the boiling point is higher. So look at the molecule on the left, a mass of 86. Molecule on the right also has a mass of 86. And the boiling point of the ketone, that is the molecule with the double bonded oxygen, is 101.7, whereas the boiling point for the alkane is lower at 63.3 Celsius. Our final slide on physical properties of molecules and how that relates to their boiling points is seen here. So we have a mass of 72 AMU for an alkane, which is N-pentane, and that has a boiling point of 36. And as we introduce an oxygen in here, which is diethyl ether, our boiling point is still rather low. If we put a OH on the end, creating an alcohol, we now have an opportunity for increased hydrogen bonding. Stronger intermolecular forces, now our boiling point raises to 117. And this can be seen through the middle of the slide, where the alcohol molecules are hydrogen bonding to one another. Now I'd like to turn to the topic of conformational isomers. And conformation, or rotamers, they're compounds with the same constitution, so the bonding of the molecule is the same, but the atoms are located in different places in space. This is because a single bond, a carbon-carbon single bond, which is a sigma bond, can actually rotate, and we can have dihedral or torsion angles. Here we're looking at conformational isomers in various structural representations. So the viewer is first looking at what's called a space-filling model, followed by a dash and wedge. The dash and wedge is very important as we then proceed to Chapter 5 on stereochemistry. The middle structure is a sawhorse with an arrow around that center bond, and that's the bond that will actually rotate. So the sawhorse structure has the middle bond which will rotate, as I've mentioned, but the position of the hydrogens is fixed. That bond angle, right, 109.5, is not going to change. So the front carbon and the back carbon will rotate, right, along that carbon-carbon axis. And that's what we see in what's called a Newman projection. In this case, the hydrogens are 60 degrees apart. In the lower case, which is a staggered conformation, in the lower case, the eclipsed conformation, you notice the difference in the sawhorse, how that will rotate, but now the hydrogens are very close together, resulting in an angle of 0 degrees in the eclipsed. So the hydrogens are overlapping each other from the front carbon to the back carbon. So this slide demonstrates the two extremes of the conformations. So the staggered, as we've said, the hydrogens on the front and back are what are called anti to each other. They're farthest apart. In the eclipsed, now they're very close to together, And this actually becomes very important when we replace the hydrogens with larger groups. And here's an extreme case in butane, where we actually have two methyl groups on the front and the back carbon interacting through various conformations. And we can see that the energy is lowest when the methyl groups are farthest apart, right in the middle, right at 180, and highest when they are eclipsed on either end at 0 and 360 degrees. So let's talk about conformational isomers with regard to cycloalkanes. The smallest cycloalkane is cyclopropane. It's a three-membered ring. Remember, the ideal bond angles for a sp3 hybridized carbon is 109.5. However, in something highly strained like this small ring, our angles change, and our carbon-carbon angle is 60, and our hydrogen-hydrogen angle is 120. And this actually will relate to reactivity of this molecule. And as we go up in ring size, we see that the cyclopentane is actually better. It's more flexible than cyclobutane. It has a bond of about 105 and is less strained. Now, the best conformation would be our cyclohexane. And cyclohexane adopts what's called a chair conformation. And we'll look at that in the next slide. So this now allows a 109-degree angle. It is strain-free. It's very common in nature. And so the understanding of this is very important. And we'll discuss this further through other chapters. So in terms of the cyclohexane, the structure on the left shows the chair conformation of the molecule. And this is cyclohexane, so it has all hydrogens attached to the carbons. You can see some are highlighted in green and some are highlighted in red. And those are different positions on the molecule. The green hydrogens are called axial hydrogens, and the red are called equatorial. So if you just think about that as a globe, where the red or the middle section would be the equator, hence those are termed equatorial. And the axial hydrogens are sticking up above the ring and below the ring. At first glance, you might think that there's not any bond rotation about a ring compound, and that's really not the case. These are all single bonds, so they're signal bonds, and a cyclohexane can undergo what's called a chair flip or a ring flip. And pay attention to this, because the axial positions as it undergoes a flip become equatorial, and the equatorial then become axial.